All right, welcome to 11.2 concentrations of solutions determining the strength of a solution. The key term in this video is going to be molarity, and you can see that spelled down on the bottom of the picture. So we're going to talk about how we can make different strengths of solutions, which is an important concept here in chemistry. To review from our last video, we had two different definitions that are probably new to us: solute and solvent. When you have a solution, you have two parts. You have the solute, which is the stuff that's dissolved, and you have the solvent, which is the stuff doing the dissolving. Now, we had said most of the time the solute, there are less particles of solute than there are solvent. The solvent is the more abundant of the two. And so you can see in the picture here, we've got the molecule that looks like a dog, the red, white, and gray molecule, which is actually ethanol. That molecule is dissolved in the solvent, which is the water. So the water is just being denoted by the blue area in the picture. This would be like vodka, I suppose. You have water and you have ethanol, and that's about it. And that creates a solution. So when we look at solution concentration, the strength of the solution in chemistry is measured in this format. It's moles per liter. So it's the moles of solute. Again, the solute is the stuff that is being dissolved per liters of solution. That's total solution. So you notice that the word solvent is not in and solution. You're going to find out. You notice that if you've got a liquid, you got some water, you got 100 mils of that water, and you put some salt in there, your volume could theoretically change. It could grow. It could increase. And so when we're talking about the liters portion or the denominator, we want the entire solution, not just the solvent. We abbreviate moles of solute per liters of solution using moles per liter. And then we give that a name because it is so important in chemistry. We give it the name of molarity. Molarity is going to be abbreviated with a capital M. Makes life a little bit convenient. You don't have to write out the word molarity all the time. And if we look at two different solutions, we've got a dark blue one on the left of the screen, and we've got a light blue one on the right of the screen. You can probably notice just by looking at the two solutions that the one on the left is going to be more concentrated because it's a darker color than the one on the right. The microscopic picture, the particle level diagram that zooms in, shows us that. It shows us that we've got more solute molecules than solvent molecules. On the left, we've only got, 4 solute molecules that are really in our picture. We've got 4. On the right, we've only got 1, 2, 3 that are present in our picture. So we are more concentrated over in the dark blue side than we are on the light blue side. Now, when we're talking about molarity, we're typically only talking about liquids. When you're talking about solids, it doesn't matter if you've got a small piece of gold or a medium piece of gold or a large piece of gold. Each one of those pieces of gold has quintessentially the same amount of molarity because it's the same number of moles per liter of gold. You usually don't measure gold in liters. For pure liquids, again, it doesn't matter if you've got a little bit of water or a medium amount of water or a large amount of water. Each one of those samples is going to have the same molarity. Now, it comes into play specifically with liquids and in gases. If you have gases, a little bit of the gas, a medium amount of gas, and a large amount of gas in the same size container, so let's call it a 1 liter container, then those gases occupy different concentrations. You have different molarity. And the same thing for liquids. In the bottom of the page, you see the sodium chloride. And on the left, you've got a little bit of sodium chloride. In the middle, you've got a medium amount of sodium chloride. And on the right, you've got a large amount of sodium chloride. I feel like I'm reading the Three Bears for some reason. That gives us different concentrations. To go back to that, I did want to point out one little symbol that we use. When we're talking about solutions, we often write a solution with an AQ after it if it's in a chemical equation. So, salt water. If the salt is the thing undergoing the chemical reaction and water is just the medium that's holding the salt, we usually don't put the water in the chemical equation itself. But we still want to tell the readers that, hey, this salt is dissolved in water. So to do that, we use the AQ. AQ stands for aqueous, and you can see it on the bottom of this slide right next to the sodium chloride, aqueous. So there are really 4 different symbols that we use when we write chemical equations next to our elements: solids, liquids, gases, and aqueous. Let's go through a practice problem for calculating molarity. So we're going to find the molarity of a 150 milliliter solution that contains 18.3 grams of copper 2 chloride. 18.3 grams of copper 2 chloride. Well, the first thing is that we're going to be looking for the moles of copper 2 chloride per liter of solution. So I always want to, when I read a word problem, I want to ask myself, okay, what am I looking for at the end of the day? I know I'm looking for molarity, and I know molarity is moles per liter. So moles of what? Well, moles of solute, and in this case, it's moles of copper 2 chloride. Now you've got to go back to your first semester nomenclature and figure out that copper 2 chloride can be written like CuCl2. And it's going to be the copper 2 chloride moles per liter of total solution. So we've got a couple of problems. Problem number 1. Our volume is not given in liters, it's given in milliliters. Problem number 2. The amount of stuff we have is not given in moles, it's given in grams. Let's look at problem number 2 first. In order to change moles to grams, obviously we're going to need the molar mass. And if we've written our chemical equation, our chemical formula correctly, for copper 2 chloride, the molar mass is going to be 134.45 grams per mole. This is going to allow us to convert the 18.3 grams into moles. And if we put it into our stoichiometry, we'll notice that we start with our given 18.3 grams, use our molar mass to convert into moles, and then at the very end, we divide by the total amount of liters. Now remember, the problem gave you the volume in milliliters, so you've got to divide by 1,000 in order to get it into liters. When all is said and done and you punch that into your calculator, you should get about 0.907 molarity. So again, what does that mean? Well, that's the concentration of the solution. If your friend made another solution but added more than 18.3 grams of the copper 2 chloride in the same volume, we would expect that 0.907 number to increase. It would be a higher value. Likewise, if they added less, that molarity at the end would be a lower value. All right, that's 11.2. Happy Cinco de Mayo.